Imagine a canyon so long that if you dropped it onto Earth, it would start right here in New York City and stretch all the way to Denver. That is a 2,000-kilometer fracture carved into a single, small world. On the opposite side of that world sits an impact crater covering 40% of the entire surface. In simulations of planetary physics, an impactor large enough to create a scar of this ratio typically delivers enough kinetic energy to overcome a moon's own gravity and shatter it into debris. Yet Tethys carries both of these scars simultaneously, orbiting Saturn today as if it were a perfectly intact world. This is Saturn's fifth largest moon, Tethys. It was named in the 19th century by astronomer John Herschel. He chose the name of a Greek sea goddess, a choice that turned out to be remarkably accurate. Tethys has a density of 0.97 grams per cubic centimeter. Because that is lower than the density of liquid water, if you could find an ocean large enough, this moon would actually float. Aside from trace amounts of rocky material, Tethys is essentially a giant frozen snowball. The mystery is why such a fragile ball of ice remains whole after enduring stresses that would threaten solid rock. The first scar is Ithaca Chasma, a rift 2,000 kilometers long and 5 kilometers deep. It makes Earth's Grand Canyon look like a minor scratch. Its origin lies in a unique property of water. Unlike most materials that shrink when they cool, water actively expands as it freezes. Billions of years ago, Tethys likely had a liquid water interior trapped beneath a solid, rigid crust of ice. As that internal reservoir froze and expanded, it pushed outward with enough force to increase the moon's total volume by roughly 5%. Eventually, the pressure became too great for the rigid shell to contain. It ruptured, tearing a jagged line across the moon. Ithaca Chasma was effectively a pressure release valve, a massive stretch mark that prevented the moon from exploding from within. On the opposite side is the Odysseus Crater. It is 450 kilometers wide, dominating a moon that is only about 1,000 kilometers across. Usually, an impact of this scale would deliver a fatal blow to a world made primarily of ice. At the time of the collision, roughly 1 billion years ago, Tethys' interior was still a partially molten slush. This soft core acted like a planetary shock absorber. Instead of fragmenting upon impact, the moon absorbed the blow, dissipating energy throughout its interior. Tethys survived the greatest collision of its life because its interior was flexible enough to yield rather than break. Even though the impact was massive, the crater today is remarkably shallow. It lacks the deep, jagged walls we see on Earth's moon. This is due to viscous relaxation. Over extreme timescales, solid ice can behave like a very slow-moving liquid. As this graph showing the crater's profile over eons illustrates, the ice slowly flowed, smoothing out the jagged edges and causing the central peak to collapse. The Odysseus crater we see today is just the flattened ghost of the original impact, smoothed away by the slow movement of ice over billions of years. In 2015, the Cassini spacecraft mapped the infrared thermal radiation reflecting off the moon's surface. The data revealed a bizarre thermal pattern that looked exactly like the 1980s video game character Pac-Man. Tethys is tidally locked, meaning it always keeps the same face forward as it orbits. This leading hemisphere is constantly hit by microscopic ice particles ejected from its neighbor, Enceladus. This continuous microscopic sandblasting alters the structure of the surface ice, changing how that specific region stores and releases heat. Tethys isn't a static relic. It is an active canvas, still being shaped and painted by its environment today. Tethys carries a forensic record of 3 distinct events: an internal expansion, a massive external impact, and a modern thermal mapping. These scars illustrate how the moon's survival depended on its internal state. A completely rigid, frozen sphere might have fragmented under these pressures, but Tethys possessed the internal flexibility to endure. By remaining soft and slushy during its most violent periods, the moon was able to absorb and adapt to extreme internal and external stress. Ultimately, Tethys survived not in spite of its icy, fragile composition, but because of it. With the Cassini mission now concluded, Tethys' remaining secrets are likely to stay hidden for the foreseeable future. But it leaves us with a question: how many other scarred survivors are waiting to be found in the frozen reaches of the Kuiper Belt? Let me know what you think in the comments. If you enjoyed this look at the solar system's greatest survivors, like this video and subscribe for more. I'll see you in the next one.